One of the chemical bond formations, specifically covalent bond formations, that we're going to be looking at is the Lewis theory. The fundamental principle behind this theory is that atoms form stable compounds by sharing their valence electrons. The goal of this sharing is for atoms to achieve an octet, which provides them with a stable electron configuration. One of the most important concepts for mastering this theory is identifying the valence electrons. These are the outermost electrons of an atom, and they are the ones crucial for the bonding process. The amount of valence electrons in an atom can be determined by the group or column number for the main group elements. Group 1 has 1 valence electron in their outer shell. Group 2 atoms are going to have 2 valence electrons. For groups 13 through 18, you're going to look at that second digit to determine the amount of valence electrons. For example, in group 13, you're going to have 3 valence electrons. Group 14, you're going to have 4. In this Lewis framework, we represent these specific electrons using a dot placed around an atomic symbol. Building on this idea of the valence electrons, we're going to look at the driving force behind the octet rule. This principle states that atoms tend to gain, lose, or share electrons, specifically to attain a full valence shell. For most atoms, this means you're going to be reaching a total of 8 electrons, while hydrogen is one of many examples where you only need 2 valence electrons to form that stable octet. In order to show exactly how these atoms bond within a molecule to achieve this stability, we utilize the Lewis structure, and we're going to touch on this in the next slide. You can think of a Lewis structure as a very simplified representation that shows how valence shell electrons are arranged around individual atoms in a molecule. In these diagrams, we use specific symbols to distinguish between different types of electrons. Bonding electrons are going to be represented by a line that's connecting two atoms, while your non-bonding electrons continue to be shown as dots. By using this method, we can effectively illustrate the entire bonding architecture of a molecule and confirm that every atom has satisfied the octet rule. Now that we understand what a Lewis structure represents, let's walk through the specific steps to draw one. The first and most crucial step is to calculate the total number of valence electrons available in the molecule. Once you have your electron count, you can identify your central atom and you can draw your skeletal structure. From there, you're going to assign the remaining electrons to the terminal atoms until their octets are also satisfied. Now, your terminal atoms are referring to those atoms that are going to be found around your central atom. If there's any electrons left over at this point, you can place them on your central atom. A common issue is that the central atom might be short of an octet. If this happens, you'll need to make multiple bonds, a double or a triple bond, by moving lone pairs from those outer atoms to the central atom to become shared bonding pairs. To finish the process and verify your structure, you must calculate the formal charges and then check for resonance. Let's apply the steps we just discussed to a specific example drawing the Lewis structure for a nitrate ion. Step 1 is to find the total number of valence electrons. Nitrogen provides 5, and each of our 3 oxygens is going to provide 6 valence electrons. That leaves us with a total of 23. However, because the ion has a negative charge, we must add 1 extra electron, bringing our total to 24 valence electrons. Steps 2 and 3 involve finding the central atom and then drawing your skeletal structure. Nitrogen is our central atom, and when we draw our skeletal structure, we'll put nitrogen in the middle and use single bonds to connect to our 3 oxygens. Step 4 is to assign remaining electrons to terminal atoms until their octet rule is satisfied. We now have 18 valence electrons to work with, 24 minus the 6 that we used to create the single bonds, and we'll take those 18 electrons and we'll fill our octets of our oxygens. We have used all 24 valence electrons, but the nitrogen only has 6 electrons from those 3 single bonds. To fix this, we're going to have to make multiple bond by moving a lone pair from one of the oxygen atoms to form a double bond with the nitrogen. This now gives nitrogen its required octet. Finally, in step 7, we calculate formal charges and we're going to check for residence. Now, this is a skill that I will demonstrate and I'll talk about more in the next slide. Now let's look closer at formal charge, which is the final step in refining our Lewis structures. In simple terms, formal charge is the difference between the number of valence electrons an atom has in its neutral free state and the number of electrons assigned to it within its Lewis structure. Our goal when drawing these structures is to arrange electrons so that their formal charge on each atom is as close to 0 as possible, as this represents the most stable and predominant arrangement. To calculate this, we use the formula shown on the slide, Fc equals V minus N minus B over 2. Here, V is the number of valence electrons on a neutral atom, N is the number of non-bonding electrons, or the dots, and B is the total number of electrons shared in bonds. Each line is going to represent your 2 electrons. Now let's apply this to our nitrate example from the previous slide. Remember, our stable structure has a nitrogen double bonded to one oxygen and then a single bonded to the other 2 oxygens. For nitrogen, our central atom, it has 5 valence electrons, so V equals 5. It has 0 non-bonding electrons, N equals 0. It is involved in 4 bonds, 1 double bond and 2 single bonds, for a total of 8 shared electrons. So its formal charge is 5 minus 0 minus 8 divided by 2 for a total of a positive 1 charge. For the double bonded oxygen, it starts with 6 valence electrons, V equals 6. It has 2 lone pairs, N equals 4, and shares 4 electrons in that double bond, meaning B equals 4. So its formal charge is 6 minus 4 minus 4 divided by 2. For a total charge of 0. 2 single bonded oxygens each starts with 6 valence electrons, V equals 6. They have 3 lone pairs, which means N equals 6, and they share 2 electrons in their single bond, so B equals 2. Now their formal charge is 6 minus 6 minus 2 over 2 for a total charge of -1. If we sum this up, we have 1 positive 1 charge, we have 2 negative 1s, and then we have 1 0 charge, which leaves our net charge to be -1, and that is the -1 that is seen on our nitrate ion.